Welcome to our lecture on energy transition. After we discussed the principles of photovoltaics last time and saw some characteristics, we want to go today for photovoltaic systems. This is an outlook on the future subjects. So let's first talk about the history of photovoltaic systems. I would call this application PV 1.0. So this was basically very remote power supply, for example, in space to power satellites or some research stations in the Amazon and so on. But even during that time, there was the expectation that in the future it will be applied to households. Here you see a scheme of a so-called solar home system. That's basically a PV generator and a string diode, which acts as a valve, which prohibits that electricity can be consumed in the generator. It only allows that the current can go out of the generator into the charge controller. And the charge controller, basically a simple charge controller, has two functions. First, to avoid deep discharge of the battery. So he will switch off the battery if the voltage is below a certain threshold voltage. So first is to avoid deep discharge of the battery. So he will disconnect the load in case of low voltage of the battery. For example, if you use a 12-volt battery, here it's typically 11.5 volts, the threshold. And on the other hand, the charge controllers avoid overcharge of the battery. So he would switch off the battery from charging if a certain voltage, in this case above 14.5 volt, will be applied. Some of the charge controller, they even have a temperature compensation. So you just added here in gray color the function of the temperature additionally, so it already takes into consideration the actual operation temperature of the battery. Here are some examples here. So on the left side you have a charge controller function, as I mentioned already. If the voltage is above 14.5 volts, then the charge current would go down to zero. And if the voltage is below 11.5 volts, that would be in danger of having a deep discharge, which drastically would reduce the lifetime of the battery. Then the load current will be switched to zero. And that's the temperature compensation. So you have the number of cells times the temperature of the battery times the temperature coefficient of minus 3.9 millivolts per Kelvin or per degree Celsius. Sometimes also you find the charge controller integrated in the inverter, as you see on the right side. Here you see the application, the market for autonomous PV systems, and that means you have a PV generator plus a battery. You see here the costs in yellow. That is for sunny locations. In orange, that's a location as in Germany. So the costs are a bit higher. Then while it's a logarithmic scale, it's not only a little bit higher, that symbolizes a factor of 2. If you go to the very left part, you see a wristwatch, pocket calculators. These appliances are usually powered by batteries. These batteries have a quite low energy content and cost some money. Therefore, the costs per kilowatt hour is really high. It's in the vicinity of 10,000 euro per kilowatt hour for energy by those battery from a wristwatch or something like this. If you use bigger batteries, for example a torch battery, then costs of that electricity is still very high, in the vicinity of 100 euro per kilowatt hour. If you would use a kettle fence battery and so on, you see that the price is decreasing. Or if you come to the generator, you have a gasoline generator or a diesel generator. Then if you have a diesel generator, the costs would be also in the vicinity of 1 to 2 euro per kilowatt hour. For bigger diesels, then the cost is going down, will be in the vicinity of 1 euro per kilowatt hour. And if you compare that to other electronics, it's still quite high. So you're not only seeing batteries, you are also seeing the options by generation by diesel or gasoline generators. See that the gasoline generator is more expensive than the photovoltaic options. Diesel generator is about in the same vicinity. If you go to the grid tariff, during that time the graphic was created, photovoltaic was still more expensive, especially if you include the storage like in this case. You see also the other option, for example, a gasoline generator of 1 kilowatt, which is including the maintenance costs, more expensive than a photovoltaic system, including storage. Diesel generator, depending on the size, is about the same costs. And for grid tariff, during that time, the graphic was created. Photovoltaic has been more expensive if you would include the storage cost. Nowadays, we are in the vicinity. If you compare the generation cost of photovoltaic systems, including storage, with the grid tariff, at least household tariff or consumer tariff. Let's take a look how we do the layout of a small off-grid PV system. First, you determine the load. So most important is that you apply the energy efficiency measures before, for example, substitute incandescent lamp by LED lamps. That makes a lot of sense. If you have done all this, then you start to calculate the actual loads and the duration of use. So you have the consumption during a day, then the determination of the battery size. So you have the load times the days of autonomy, DOA. For example, as a rule over the thumb, you have 4 days in Germany and 2 days in the tropics. It depends how long bad weather periods take and so on. It's really not completely a night there. You still have some production even at bad weather, but you can apply 4 days in Germany and 2 days in the tropics. Then you have to take care on the maximum depth of discharge. For lead-acid battery, if you want to have an acceptable lifetime, it's in the vicinity of 50%. If you go to the lithium-ion battery, you can still use 80 or 90% of the battery's charge. Then you calculate the size of the battery, so that's the energy consumed by the load times the days of autonomy divided by the depth of discharge. Then you calculate the energy to be generated by PV, including all the losses. So you have here the actual load divided by the efficiency of the charge controller, divided also by the efficiency of the battery, and also divided by the efficiency of the inverter. Then you take a look at the daily irradiance at a typical day of the worst month during a year of operation. Either take it from own measurements or from tables or from simulation. So you have this worst day and divide it by the area, and then you can calculate by that the area of the required PV generator. That's the energy of electricity, of photovoltaic electricity to be generated during a day, divided by the photovoltaic conversion efficiency times the irradiance per square meter or not area during that day, typical day of the worst month of the year. So you can determine the power under standard test conditions. That means under 1000 watt per square meter. So you have here the irradiance under standard test conditions times the area of the photovoltaic generator times the photovoltaic conversion efficiency, and then you have here the irradiance under standard test conditions times the energy to be generated by the photovoltaic generator divided by the irradiance value during typical day at the worst day of the month divided by the area. What are important points for PV implementation? So that's project identification. So you have to know the irradiance on site, the land, the security. Do you have spent something to make a fence or not? How is the grid connection? How far is the grid connection? Are you allowed to do grid connection? How much would it cost? And the legislation for grid feeding. Usually you get a PPA, that means a power purchase agreement, so you know how much is paid for your energy. Financing, as I mentioned already, the PPA. Carbon trading plays an increasing role. For the case of Germany, after the 1st of January 2021, you will get 25 euro per avoided ton of carbon dioxide. Other countries have more. For example, Switzerland, it's a vicinity of 80 euros per ton of carbon dioxide, or Sweden, 150 to 120 euro per ton of carbon dioxide. Taxes or tax reduction, subsidies, interest rates plays an important role, and inflation. Equipment, you have to take care that the components are suitable for high operating temperatures, depending on the site, high sand and salt contents of the air, ultraviolet stability, and the warranty. Important that warranty should be given by a local dealer, not somewhere in China and so on, because nowadays the costs for dismantling and sending in to the actual manufacturer is more expensive than to buy new models. Infrastructure, so you should keep an eye on the requirements for importations, not only cost but also time, transportation, the mounting equipment, tools, accessibility for the location of installation, especially if you have remote places, installation team, the training of a local supervisor, maintenance, financing and training, problem management, future development of demand. It also plays a key role, because if these local people see that there's electricity available, they possibly will buy a TV set or a washing machine or something like this, and soon your layout of the system or microgrid will be too small, and then you have to extend that. You have to either already include this in your calculations or at least offer the possibility to expand it. Also quite important, often neglected, are non-technical issues for photovoltaic implementations. Culture. Sometimes short-circuit solutions are often preferred, because the photovoltaic systems, you pay the electricity supply for the future 25 years up front, while if you would use a battery or a diesel generator, which has a shorter lifetime, but the costs are much less. So there you have to provide a solution, either lend the photovoltaic generator or offer good financing. Often there's a focus on centralized, large-scale, spectacular solutions, especially by the local government there. For example, nuclear power. It's not only about energy option, it's actually quite expensive. It's also because it's prestige, let's say. So this is, if you have a nuclear power plant, it's likely that you appear more in the newspaper rather if you would open a solar power plant or so. Deficits in education. So in general, the politicians are not engineers, so they hardly know about subjects and they don't know about the actual price development. They still have in mind that photovoltaic is prohibitively expensive. That's not the case since a decade. You have to convince them that that's not anymore the case. Legislation. So for many off-grid sites, there is a subsidy, but only for diesel because they disconsider photovoltaics. Sometimes there's also corruption involved because diesel is not only the sales of the diesel engine, there's also a lot of maintenance, there is transportation of the diesel fuel, and these are well-established structure and many families live from that. And if you come with photovoltaics and would break those chains, people are not happy sometimes. Long-term financing, that's a lesser problem in Europe, but if you go to many third world countries, they have very high interest rates. Sometimes it's a vicinity of 30% per year. Missing marketing and lobbying, so people hardly know about the possibilities and the options of photovoltaic power generation. Let's come to mounting. So we discussed a lot about the photovoltaic principle, the modules and so on, the photovoltaic generator. Now we have to put it on the ground or put it on the roof, and this will be discussed in the next 10 minutes. But interesting, if you see the cost structure, you see here that 20% is only for the solar cell technology, another 20% for the silicon wafer, 25% for the module. But the really high share of the costs are installation, support structure, land, ground preparation, inverters and so on, grid connection or battery. And this is usually called BOS, balance of system costs. And these in average are typically amount 35%. It even increased because the module prices went down, and nowadays you even find BOS costs in the vicinity of 50%. So what do you have to consider at the mounting structures? So you have to know the technical specifications. What are they? So the material, steel, aluminium or wood. Sometimes wood is quite a good option. For example, if you go to marine areas which have a salty air, and this is very aggressive to metals, but not so to wood. So sometimes the wood is a more longer lasting option than the metal construction, but it depends really on the application. Simplified maintenance, so this is also a cost which is often disconsidered. Corrosion resistance in a moist event, aluminium or used galvanized steel. Not powder coated, but at least hot dip galvanized steel. Variable height and variable angle, because the ground sometimes is not even, so is a foundation, and you have to level that out by variable height of your substructure. Accuracy and tolerances. There's a high competition nowadays, and so the manufacturers spend little time on really manufacture the equipment very accurately, and so you will always have some tolerances. Effort of installation and effort of disassembling. If you dismantle the power plant, is also considered in the total costs over lifetime. Also, you have to take care about lightning and adequate grounding. Integration of the cable layout. There are different requirements in different countries. For example, in the US, you always have to have the cable within a metallic tube. That's not required in Europe, and so on. This has an impact on the total cost of the system. Wind load is very much site dependent. Compatibility with PV modules, so you have to take a look whether the size of the subconstruction and the position of the screwing balls is adequate in accordance with the PV modules. Constructive construction, fixture of the modules, module arrangement and the wiring. Mounting structure shall be able to neutralize slightly unevenness on the ground, I mentioned already. Here I have you some examples. First example is the fixation of the external edge of the modules. If you are in between two modules, to come to solution 2. So this fixes 2 module edges. The fixation between the module and the transversal bar you see at number 3, or fixation at the foundation pile you see on picture 4, and also on the 2 photos. You see that they have some tolerances. They can even be tilted in order to allow adaptation. The more modern one, these are so-called ground screws, so you can install much quicker, or you have hammered piles. Sometimes this is even automated, so you have a robot which knows exactly the position and drives in a pile automatically. So you see here a movie about that, about the company Grinner, which perfectionized this mounting by ground screws, and you just can install a very large-scale power plant, in this case a 330 megawatt system, within a very short time period.
Just half an hour by car from Bordeaux is one of the largest photovoltaic building sites in the world. The modern high-tech solar park extends over an area of 2.6 million square meters, the equivalent of 363 football pitches. Thanks to the maximum output of 300 megawatt peak, approximately 111,000 households can be effortlessly supplied with electricity. As a result, approximately 230,000 tons of CO2 are saved each year in comparison with a coal-fired power station. For this mammoth project, the Lower Bavarian family-run company Grinner took over the planning and realization of the foundations and installation. The specialist for ground screws will complete the solar park in just 8 months of construction. The precise project preparation is the cornerstone for the rapid construction period. With help from special machinery developed by Krinner, time-consuming and cost-intensive risks can be calculated in advance. In the first step, the soil conditions are inspected to guarantee long-lasting stability and fastening of the foundations. In the second step, a GPS-controlled measuring robot creates a detailed site plan on which the markings for the ground screws are placed with millimeter precision. This allows precise and rapid positioning of the foundations and is the basis for the absolute adherence to delivery dates. The collected data is inspected and fully documented at the Krinner headquarters. The data is then transmitted directly to the on-site construction machinery via the Krinner cloud. This means the foundation work can begin without delay and with the utmost precision. The ground screws are screwed into the soil with millimeter precision. The fully automated process and the special ground screw drivers developed by Krinner make it possible to position the ground screws rapidly. The material-optimized patented design of the support frames adapts perfectly to the local conditions. As a result, Krinner can guarantee a high level of stability, low costs, and rapid installation time. Finally, the photovoltaic panels are quickly and easily assembled with a plug-in system developed especially for this purpose. Thanks to cutting-edge technology and efficient working steps, more than 4 megawatt peak per installation team can be assembled each day. In addition, the support frames are completely maintenance-free after assembly, which means no subsequent costs. To us, top-rate performance does not just mean extraordinary quality and reliability. It also means extensive checks. For this reason, we check our products exhaustively before approval, providing you with the security you need. Especially in terms of the project costs, our customers benefit from rapid commissioning, freedom from maintenance, and rapid amortization. 200,000 ground screws, 326 kilometers of support frames, almost 1 million photovoltaic panels. With a solar park in Cestas, the inventor of the ground screws created one of the largest solar parks in the world in an incredibly quick construction period. Thanks to Krinner, quality made in Germany.
Here you see some equipment for smaller scale PV power plants, for example, on roofs. So they are tools and specialized mounting equipment, for example, to adapt it to roof tiles. Also there are special equipment to allow the penetration of cables without affecting the waterproofness of the roof. Modules which don't have a frame, so you use mounting clamps. This saves also costs for the frame. So here you see such a mounting clamp for frameless modules. So here, even with one screw, you can fix 2 modules here. Here you see some examples available in different sizes, in different area. It's important to obey to the requirements of the manufacturer of the modules, from the area of the clamps to the position of the clamps, because sometimes high wind loads could lead to breakage of the glass. So usually frameless modules are quite sensitive and you have to install more cautiously. Some examples of nice integration in roofs and so on. Here facade. Also here is a double function, so you have the PV modules and they are also a shading element of the summer sun in order to reduce air conditioning costs. Here you can also control the light by use a different density of the solar cells. Here you see in between the solar cells there's sometimes more space, so you have more in-room light, or less space. If you go here on the left part, you see here that appears to be darker. This is in North Rhine-Westphalia in Herne. During that time, it's one of the biggest roof integration with 1 megawatt in 2002. Here you see that. During that time, it even entered in the Guinness Book of Records because it covered an area of 10,000 square meters. The mother is a fixed mounted 6.6 kilowatt, and on the right side on top you see a 2-axis tracking system, so you follow the sun by that. It's also in large scale. Became a bit silent about this tracking system because the costs for tracking have been quite expensive. Nowadays they're getting more interesting because the use of tracking system is more grid friendly, so you can generate more power also in the morning or in the evening. While if you would have a fixed system, it only generates maximum power usually during midday. You will see the azimuthal tracking and the tilt tracking on the right side. Here you see an application which has been used for almost 2 million houses in Germany. Grid-connected PV system. You have a roof covered with PV or partly covered with PV. Then you have a junction box where all the modules are connected, either in series up to a voltage of 1000 volts or 1500 volts, and then in parallel. Then you have the inverter. And you have a kilowatt hour meter or counter for consumption and PV injection, grid connections, and what just becomes more attractive during the last years, local loads, because you can generate electricity cheaper than you have to pay for electricity from the grid. The essential part was an effective feed-in legislation. So you get a fixed tariff, you can do your investments, not only for you, but also for the bank if you want to lend money. And you see that you have a legislation for grid feeding and you have a fixed income, and they are more likely to give you an attractive credit rather than when the income situation is unknown. Here are some examples. Here is a so-called plus energy house. So these houses produce more energy than they consume. It's also the Munich airport, 2.2 megawatts. It's also 11 megawatt power plant in Serpa in Portugal. This is a 67 megawatt power plant in Germany at an old military airport. This technology also creates jobs in quite different areas. For example, here, this is the startup which makes cleaning robots for cleaning PV arrays. This parallel connection of PV strings, so this we already discussed in the exercise. This is string diodes, so you put string diodes as a kind of valve, so which allows only that current can escape from one string rather than to enter one string. For example, if the strings have different voltage, maybe due to shadowing conditions and bypass diodes, you want to avoid this, and by this you put string diodes which block the current in the opposite direction. The most simplest construction is you have a series of modules interconnected in series. As I mentioned, usually the maximum permitted voltage is 1000 volts. Formerly it was 600 volts. Nowadays it goes even up to 1500 or even 2000 volts. You connect them in series and have a DC switch before the inverter, and then you interconnect it to the grid, either single phase or most often use triple phase. Here you see that you put in a different sequence to balance out. Module inverters, it came up the last year, so you have an inverter for every single module, which provides a redundancy of the inverter. So even if one module or one inverter is defect, the rest of the power plant is still continuing to operate. This is a DC connection box in China, which operates with a PV generator of 127 kilowatt peak, so under standard test conditions. And this bundles all strings via protection fuses, not string diodes, because it's more expensive and you have some voltage losses, as we already found out in the exercise, across the string diodes. And so in order to save costs and avoid losses, it uses fuses. Let's take a look inside that connection box. So you see here the cable from the PV array. It operates not at 1000 volts, but at 700 volts. Here the positive and here the negative poles. Then you have the fuses here. Then you have the DC switch, and you have here lightning protection. And then you have the output here, which goes into the inverter. Can calculate those losses by these formulas. There will be also an exercise to that. Inverters are quite important because they provide the intelligence of the PV system, so you can control the whole PV system basically via the inverters. So most often in the inverter that's included a MPPT, means a maximum power point tracking device. So it adapts the virtual resistance to the maximum power point, so you can extract the maximum power from your PV modules. It keeps it working in the maximum power point, even at changing temperature, or most important, at different irradiance level. And then you have the actual inverter, which transforms the DC into a synchronized AC to the grid. Here are some examples here, very simple inverter with 4 switches. What you usually do nowadays is PWM, pulse width modulation. So you adapt the length of a pulse according to the required current. So if you at the top of a sinoid, the pulse is almost permanent, while if you pass through the zero, then the pulse is extremely short. If you soften those pulses, then you will arrive at a sinoid. The softening is done via a filter. So this is here a filter. You have an inductivity in series and a capacitor in parallel. This is a transformer. Usually in order to save costs, it's not so frequently used anymore, and you just directly operate with the grid voltage. So you can avoid the cost of the transformer. This is for a 3-phase system, works similarly only with 6 switches. So only always a switch for the positive and for the negative part. What is often done is to operate at an artificially high frequency that saves costs for the transformer. The transformer can be much smaller, the iron core, because the frequency is much higher, and so you can use a ferrite, and this makes the transformer much lighter and less costly. And then you transform it back to the 50 Hertz sinoid later when you are at the correct voltage. This is an example for the European efficiency of an inverter. So you have here in red the curve here, the efficiency curve. And then instead of taking one value only, you take a weighted mix of all the values. So the weighting is 20% for the maximum power output. Then, because it's much more frequent, you have only half of the irradiance or less. Then you weight that with a factor of 0.48 or 48%. And then you have even for lower power 10% and 13%, 6% and 3% as a weight. And then you end up at the so-called European efficiency. This is important because formerly often only the maximum power has been applied. That means an inverter which apparently has a higher efficiency at 100% of the relative load only. But if you go to partial load, then, for example, here in this case, inverter 2 may be better because he offers a higher efficiency at partial load, which happens more frequently in Germany. If you go back here to the slides, this is a formula to calculate the weighted European efficiencies, as you saw before on the graph. And here you see a frequency distribution of the different irradiance levels. So you see your standard test conditions happens relatively seldom, a bit more if you have minute values. Sometimes there is a bright spot and you have for some minutes you have really 1000 watt per square meter. If you use the hourly values, it's really seldom that you achieve standard test conditions at the radiance level, 1000 watt per square meter. So in the vicinity of 5-6% of the year. Most often you have here a radiance level in the vicinity of 300 to 400 watt per square meter. That means 30 to 40% of the actual maximum load, which is usually the inverter usually designed for. So here in this vicinity, P30, so this is most relevant here for Germany. By knowing that, you can also save some costs by thinking about the relation between inverter and PV generator, because most often the inverter doesn't have to digest the nominal load. For example, if you have a 1 megawatt PV generator, it's very seldomly it produces really 1 megawatt. So if you would use an 800 kilowatt inverter instead, would be considerably cheaper and you wouldn't lose a lot of power. So if you go, for example, here to the relation inverter to power output of PV generator, that would mean in our case for 1 megawatt PV generator and only an 800 kilowatt inverter, come to this curve. And for the case of Germany, would still have an energy yield of 99.3% of the original output. So you would only use 0.7%, and you would possibly save 20% of the inverter costs. The different configurations, as we saw already. So this is for a 3-phase system. So each phase has a separate inverter. They have to be synchronized in such a way that they have a phase difference of 120 degrees for each phase. And here you see this configuration too with multi-string inverters. Sometimes you see also this configuration. For example, you have roofs with multiple orientations. That would mean that some part of the roof works better in the morning hours, another part in the midday hours, another part in the evening hours. And if you would put all in series, the part with the lowest performance would determine the overall performance. Therefore, it's important to keep them separate. So we can keep them separate by giving them an extra inverter for each part, or at least a separate maximum power point tracker as shown here. And later you use still one central inverter, but this allows a much better performance and is a little bit cheaper than if you would have 3 separate inverters for the 3 cases. So also the master-slave concept is quite interesting, because if you during winter you hardly reach the nominal power, only a small part of it, and then it might be preferable that you use a smaller inverter which operates close to its maximum power output and with a high efficiency. If you need more power, you would call a slave, and then you bulk that power of the different inverters until you reach the actual power output of the PV generator. Here you see that. So one inverter alone has the orange curve. So for partial load, especially below 20% of load, then the efficiency gets really bad. If you have a master-slave concept, you even at the partial load of 20%, you have a quite good conversion efficiency. There are 3 inverters in a master-slave concept. You see a blue line here. Module inverters, I mentioned already, they allow redundancy. So you have each module has an own maximum power point tracker with an inverter. In case of shadowing, only one module is affected. We modules here in Paderborn here. We made some publications on it. If you're interested, you can see the comparisons. Just as a quick overview here, you see here the comparison of different inverter configurations. So you have the string inverters. They go up to a voltage of 1000 volts. So power is not more than 100 kilowatt or much less. Efficiency goes up to 98%. Market share is 37%. The most often used are central inverter. So you have one inverter for the whole power plant, and it's usually the cheapest option in the vicinity of 10 cents per watt. You have a high reliability. The microinverter, that means you have an inverter for each module. It's the most expensive option, but it's easy to install and easy to replace, and you have a lot of redundancy. And what we saw before for the multi-orientated roof, these are so-called power optimizers. So each section of the PV generator has its own maximum power point tracker, and together it goes to the kind of central inverter after the maximum power point trackers. System layout for grid connection. So you here see some layouts as we saw before. So we have the PV generator, several strings. They get connected in parallel within the junction box, as we saw before the Chinese example with 127 kilowatt examples. And you have either string diodes or fuses. Then you have a lightning protection, and then you have a cable which goes to the inverter, or before that DC main switch, which was integrated in that junction box as we saw before. These are some typical diameters which you would use. For systems with a larger power than 30 kilowatt in Germany, you have to have an external switch, so you can be switched off remotely. For large system configuration, not only going to the low voltage grid, you're going either to the mid voltage grid, or for a very large system, you even go to the high voltage system, for example, 110 kilovolt or even 380 kilovolts. There you can perform several tasks for the grid, so you're in contact with the grid operator, so you can provide dynamic grid support, you can provide static grid support by using reactive power, and so on. So this is a medium voltage grid connection with a transformer, what you see here. This is a high voltage grid connection, 110 kilovolt in China with a 100 megawatt system. See that the prices went down constantly of PV modules. You saw it in the lecture also before. For the cost, you have to consider first the module cost, efficiency and technology, module properties, but also you have to consider the module properties, warranties, and so on. And local conditions, you have to have the array orientation, possible shading, snow and wind loads, soiling, for example, by clay, rock, dust, and so on, and the adequate grid connection and the site layout. You have also, as I mentioned, the balance of systems costs. That is usually also defined as same as photovoltaic modules in euro per watt peak. It depends on substructure, the foundation, inverter and monitoring, cabling, connection, engineering, procurement and construction. The abbreviation for that is called EPC, margin and other things. Take a look at the balance of system costs. So you have the mechanical balance of system costs. This includes all mechanical parts for the installation for the photovoltaic power plant. So that means substructure, mounting parts, and so on, labor for the foundation and assembly. Then you have the electrical balance of system costs. That includes all electrical components to connect and combine the PV modules, string and so on, and labor for work of assembling and installation. So this is a bit old picture, but still valid for small systems. Formerly, it was about 55% you spent on the PV modules, then about 13% for the inverter, about 16% installation material, and for the actual installation, you paid about 11% of the total costs. This changed, we will see a graph to that. So while the modules always got constantly cheaper, but the labor and so on, and the installation and installation material also was rationalized, but not as much as the photovoltaic panels, and therefore the share of the photovoltaic panel went down considerably of the total cost. Ground-mounted system. So you see here, if you have a high efficiency solar cell, you need less area and also less installation material, but the module costs have a higher share. This is the case A. If you go to the right side, for example, to M, you have a thin film TF, thin film silicon PV module which has a lower efficiency, is cheaper, but requires more area and more wiring, more space for installation and more mounting equipment. And therefore the share of balance of system cost is considerably higher. Here you see the different cost shares of substructure, mechanical installation, electrical installation, and so on, inverter and EPC. So remember, engineering, procurement, construction. Here you see for the different mountain types, GMS means ground-mounted system. So you see here the different shares. So the most costly then is a substructure. If you go to the middle part, then if you have already a pitched roof, then the substructure is considerably cheaper, but you have more labor costs and so on. Almost the same applies for the right part, which is a flat roof construction. Here you see the development of the prices of a complete system. So we are already now below $1 per watt. Here you see the price development. This is from 2016. Actually, the prices are a little bit lower than predicted during that period. Here you see the impact of photovoltaic on the load curve of an energy system. So you have lowest consumption at 3 o'clock in the morning and highest consumption in about midday. So here you see the load curve and the photovoltaic generation curve. This was for 39 gigawatt. Nowadays we have 50 gigawatt of photovoltaic installed. So you see here the base load, and then you have middle power plants. This traditionally have been hard coal power plants, while the baseload power plants have been nuclear power plants or lignite power plants. And for the peak power plants, usually more expensive but more flexible gas power plants have been used. Due to the penetration of photovoltaic energy, the gas power plants are less often used because they produce a power during a midday, and this leads to a lower full load hours during the year of the gas power plants and makes them more expensive. Here you see the generation in Germany during the first year of 2014. So you see here considerable part, especially during midday, has been realized via photovoltaics. As you see here, the price drops here at the end of the week due to the high share of renewables, even negative prices, because the traditional power plants as lignite or nuclear power plants cannot keep up with the high penetration of renewables in the grid systems. They always have to have a minimum load, and sometimes that's not possible. So they prefer negative prices, so you are paid to consume more. So here you see a day in 2013. You see here the generation curve and the according prices on intraday during 1 hour day ahead. So you see the bouncing of the prices in general. You see that at midday nowadays we have almost the lowest prices, while in the morning and evening a price get up because there is less photovoltaic energy available. So you see here, as the photovoltaic goes up, prices go down. Nowadays we should think about that. So we should, in order to avoid high price in the morning and the evening, we should produce more solar power in the morning and in the evening. And this you can do by tracking or by selective coding, so angular selective coding. You see this one, you see the price of time of day between 9 and 10. We have the highest price of the period with the highest price of electricity. And this is equivalent if you have a south-orientated module with an incidence angle in the vicinity of 40 degrees. And if you could do a structure on the PV module, you see here that for this vicinity of incidence angle, you should have a structure with a 90 degrees of a V angle here. And by this you have an increase in power output. Also, you can tilt the modules towards east, then you have more power in the morning, or tilt it more towards west, then you would have more power in the evening hours. You can also modify the seasonal production by inclinating the modules more steeply, so they would produce less in summer, a little bit more in winter. It doesn't look a lot here in January because the general level of photovoltaic energy production is quite low, but actually it's 21% more of PV energy in January if you would incline the PV modules to 60 degrees instead of 30 degrees. In summer, we would have a loss in the vicinity of 15.7% during that month. Also, you could do some thermal conditioning. So this means you put a phase change material into the module, and this melts quite slowly. And in the morning, you have a colder operation temperature. That means you would have more power output. The evening, that is vice versa, because the module stays a bit hotter than it would be, so you would have some power loss. But by these measures, you can adapt your power production during the day and during the year. There are also some exercise to it here, for example, the wiring. This will be discussed later. Thank you very much.